You're watching The New Stack Makers, a podcast for people who develop, deploy, and manage at-scale software. For more information and articles about at-scale technologies, please visit thenewstack.io. Now enjoy the show.
Since its inception, Amazon Web Services, AWS, has been the best place for customers to build and run open source software in the cloud. AWS is proud to support open source projects, foundations, and partners.
Okay, today I am with Patrick Ames, who is a principal engineer at Amazon Web Services. Hi, Patrick.
Hey, Alex. Thanks for having me here.
Yeah, I was reading on LinkedIn that you were recommended by one guy one colleague of yours, because you were the go-to guy. He said, you could answer the questions. Have you always been curious about stuff, so you learn a lot about it? I mean, is that something you can think back to when you were a kid?
Yeah, I guess I've always approached things with a certain goal in mind, right? I wouldn't say that I've been a person who's always set out on engineering projects or other pursuits of curiosity without some ends in mind, right? So, here at Amazon and in other projects in life, it's usually just me learning what I need to do to get past some problem that I'm having or to make something easier in life for myself, right? So I'd say I've taken a very kind of goal-oriented approach to engineering over the years, where I'm looking at some problem, looking at something that is difficult to do and trying to find out ways of making it less difficult or easier to approach that sort of problem. So a goal-driven pursuit of curiosity throughout my life, I suppose.
So to make things easier in your life. So does that mean around the house, you try to make your house easier to use or stuff like that?
Yeah, sure. Yeah, I mean, simple things the more your house is organized, right, the easier it is, the more you've sorted all the things in your house to actually go and find things. I try not to obsess over it too much, but I suppose that would be my natural compulsion.
Yeah.
To have everything organized, to not have to vacuum the floor every day. I'm very excited about the invention of things like robo-vacuums, right?
Yeah.
I haven't invested in it myself, seems a little too dangerous, but I've seen things like robo-lawnmowers and other things like that, which seem like a bit of a line where you're crossing automation with potentially dangerous technologies. But stuff like that's pretty cool, right? You got daily chores, you got daily things you want to do. How do you make that easier? How do you make it more painless? How do you make it more fun, too?
I love that. I mean, it kind of gets to the heart of what your work is, doesn't it?
Yeah, absolutely. Software engineering at its core, I feel is just an exercise in reducing a lot of redundant manual labor that you otherwise have to do by hand, reducing the act of thinking through the same problems over and over again by codifying an approach to solving them and then revising that approach and making it more optimal over time. So instead of just approaching the same problem, and I think there's, a lot of virtues in being an artisan and in perfecting your craft and in being able to do the same thing perfectly over and over again, like a chef or something. And technology isn't, as far as I'm concerned, anywhere close to replacing them. But as far as, computational tasks historically, and these days with generative AI, creative tasks as well, I think we've seen some very interesting things and interesting ways to take a lot of that manual redundancy out of our daily lives. Yeah.
So, our topic is there was this move from Apache Spark to Ray data, right?
Yeah.
And why the exabyte scale migration, took the time that it did. I love these kinds of stories because they get to the heart of how you build things and the trade-offs you make and decisions you think through. So I just would love to talk about the project, and how did it come about, and why, and get into a little bit more about it from there.
The origins of this project are kind of tied back to when I joined Amazon in 2016. And back then, Amazon was working on deprecating a very large Oracle data warehouse that it was using for data analytics and all of its business intelligence use cases. So I participated in that migration and helped build a service that literally copied all of the tables and all of the bytes out of Oracle and put them in an S3-based data catalog. And at the time we copied them out of Oracle, we had about 50 petabytes of data resident in S3 that quickly grew to exabyte scale. And 4 or 5 years ago, it turned out that we were using Apache Spark to do a lot of critical table maintenance on all of that data. So the way our catalog was set up, to give a little bit more context here, was we have a collection of data producers across our various businesses at Amazon. These data producers are typically putting insights about their business into the data catalog. So these insights arrive in the form of S3 files. Maybe they're Parquet files, maybe they're delimited text files, typically two-dimensional tabular data of records to insert, update, and delete. Like I think an easy to understand example is that of tracking customer orders. A customer order enters the system for something like the Amazon.com retail website. Maybe in the initial status, it's pending some sort of fulfillment. And then it gets transitioned into a shipping state, and then eventually the shipment arrives. And you can imagine this various transitory states that this order goes through all being kind of updated in this table, tracking each state that it went through, when it went through that state transition, from the order being placed, to the order being shipped, to the customer receiving the order. Kind of a simple example.
So tracking the state.
Right, of how business data, for something that we might all interact with in our day-to-day lives on Amazon.com, can be turned into just a tabular data set and then ingested into the system.
Right.
So obviously lots of orders are going through the system, lots of other things are happening on Amazon. It's a big business, it's more than just retail, it's Alexa, it's released various devices over the year, Kindle, ebook readers. There's a lot of different business segments of Amazon's, which means a lot of data to collect here in this business catalog. Our business catalog quickly grew to exabyte scale, and so lots of business inserts, updates, and deletes tracking these types of insights about what's going on in all these businesses are arriving at such a great volume that we've now got exabytes of inserts, updates, and deletes to read out of our catalog.
Right.
So when people write these data to our catalog, well, somebody has to read it back out.
Right.
And in order to read it back out, they have to merge all the inserts, updates, and deletes into a final table state to query using something like SQL or using, say, like a Spark data frame. If you're in the Python world, a Pandas data frame, something that the end consumer can use to understand what's going on with a particular business segment.
In our discussion, we're talking about Spark. Why did you choose Spark in the first place?
So Spark was obviously very popular in open source at the time that we started investigating it. And it turned out to be very easy and very simple to stand up a working application that would actually merge all these inserts, updates, and deletes with a few simple lines of Spark SQL. So it was very easy when we took a look at Spark to get kind of a proof of concept implementation of creating a read-optimized table for our consumers off the ground. Because if you had these consumers spread across all these different compute frameworks like we did, we had consumers using compute frameworks like Redshift to read the data, and Apache Hive in the early days, Flink, kind of whatever their favorite compute framework was to query the data, Athena. If you just built up inserts, updates, and deletes forever, eventually they reach scaling limits and they're going to take hours or days or longer to actually complete the merge and to get the table in a readable form. So Spark entered the picture as a way to periodically cache the result of merging all these inserts, updates, and deletes. It was kind of designed for this decoupled model of operating over data stored in S3. It wasn't a coupled model like historic data warehouse databases of storage and compute.
What trade-offs did you have to make with Spark, and how did those trade-offs then change the way you think about using Spark and using Ray instead? When
we first started using Spark, it was operating pretty well for us. You know, we went through some growing pains with it. The initial proof of concept SQL statement that we wrote had to be productionized, and we had to get serverless job management infrastructure implemented around running Spark at scale and managing thousands of Spark jobs every day, which means thousands of different Spark clusters every day. So there were a lot of growing pains, from proof of concept, yes, Spark can do this job type, to, okay, now manage thousands of Spark jobs doing this job type every day. And initially, you know, Spark was usually merging all the inserts, updates, and deletes on table partitions that were typically no larger than, say, terabyte scale in terms of data at rest in S3. And this would, again, be maybe gzipped delimited text or Parquet data sitting in S3. And at that scale, we didn't have too many problems. But once individual partitions of inserts, updates, and deletes, or unpartitioned tables of these same change data capture logs grew to, say, hundreds of terabytes or petabyte scale, we were again encountering this familiar scaling problem of, okay, Spark jobs are taking an onerously long time to complete. Data consumers are complaining that it's taking too long to receive their data insights that they need to run their business. And it's also costing us too much money just to run these gargantuan Spark clusters in order to merge all these
really
inserts,
costly?
updates, and deletes day after day after
Because
day.
it's update after update after update.
Right. So we started thinking like, well, Spark is a great general purpose data processing platform, but they've never, in being a general purpose data processing platform, it's kind of always an enemy of being a specialist in any one particular domain, right? Just like GPUs can do floating point calculations a lot better than a CPU, but a CPU is much more general than a GPU.
Exactly.
Spark is very good at general purpose data processing and doing any job you want, generally good enough. But if you have one particular job type like this that does the same thing day in, day out, at scale, and it's costing you so much money, it's probably wise to look into a specialized approach.
Yeah, did that happen then? Did you see that? Were there specific cases that really required, that made the Spark more, less applicable than it could be?
Yeah, kind of. I mean, we would do a lot of analysis of it. We'd look at sort of the execution plan, how it was planning on approaching the problems that we'd give it, and we'd pick it apart, and we'd find areas where we thought we could optimize the execution plan and say, okay, well, it's not a bad approach, but if you were taking a theoretically optimal approach to the problem at hand of just applying inserts, updates, and deletes from S3 every day, and if you furthermore know that those inserts, updates, and deletes are largely Parquet files and sometimes gzip delimited text, you can start to pick areas of specialization to get down to. And if you also know that they're indexed in some sort of catalog similar to Iceberg or Hoodie, like we used internally, then you can use even more tricks, like keeping track of clean or dirty files that were touched or untouched by this process and copying by reference when possible. So there's just a long list of improvements that we built up that we wished we could have made to the default Spark execution plan. And that led us to investigate alternatives to Spark.
So you started looking at Ray. And what were some of the things that you were hoping that Ray would alleviate that you were discovering with using Spark?
So
maybe you could talk about Ray a little bit, what it is for people who may not be familiar.
Yeah. Maybe like a brief intro to Ray, which is also why we started looking at it. So Ray came out of a research project at UC Berkeley Rise Lab. It was formerly AMP Lab, which Spark came out of previous to that. So our attention had been drawn to it somewhat just because of the people researching it, being the same people that had worked on Spark before over at UC Berkeley. But Ray was focused on solving a different, more general set of distributed systems problems than Spark. And it started to additionally narrow its focus into machine learning over time and solving kind of hard distributed machine learning problems at scale. which are now, very popular. They've exploded in popularity over the past couple years. But underneath all of this was a very general purpose distributed computing framework called Ray Core. And on top of it, to attract data scientists and machine learning engineers to the platform, they had built kind of their flagship APIs in Python, since most data scientists, machine learning engineers, and machine learning scientists are most familiar with Python and are doing most of their work in Python. So it was this new Pythonic distributed compute framework that could distribute, in theory, almost anything. At its core, Ray just consists of two fundamental primitives. One is a task, which is just a distributed function, and another is an actor, which is just a distributed version of a class.
Yeah.
So anything you can describe with functions and classes, which is pretty much any application that you write, you can distribute with Ray at its core level. And then it has specialized APIs for machine learning.
So then you started this migration process with Ray, from Spark to Ray. What did that require you to do? What architectural demands did it put on your team? What were the things you needed to do to make sure that this transition went effectively?
There was a lot. We started with just some simple experiments with Ray, right? I fired it up and threw some arbitrary distributed systems problems at it and just observed, how many tasks it could schedule per second, whether or not it would consistently deliver correct results, how effectively it was able to auto-scale clusters, request additional EC2 resources on demand, return unused EC2 resources when it was done using them. So the initial set of experiments went well. We said, okay, it looks like a pretty legitimate distributed systems management framework. And indeed can be used for both machine learning and more general distributed systems problems than just machine learning. So we developed a design that was effectively made for Ray of the compactor, as we called it, which was this process that applied the inserts, updates, and deletes on Spark and created a read-optimized version of tables for our business intelligence consumers to consume. And then we made an implementation of that design of the compactor, which we called the Flash compactor on Ray. We contributed that back to a Ray ecosystem open source project called DeltaCat, which provides data catalog interfaces for interacting with these tables, which we implemented for our internal data catalog at Amazon. After creating this implementation and proving out that it worked on a single job level, and then proving out that it worked at scale, at terabyte scale, at petabyte scale for some of our production tables, we started the process of making large-scale serverless job management for Ray clusters that could run, again, similar to Spark, thousands of Ray clusters a day, fulfilling thousands of jobs a day, and each one of those clusters may contain thousands of EC2 nodes doing the actual processing of terabyte and petabyte scale individual tables and table partitions containing all these inserts, updates, and deletes to merge again to create your read-optimized tables.
What did you find out of it? What were the efficiencies that you found from it? Because that was one of the things you were looking for from Spark.
After we did several months of production shadowing, as we called it, of Spark jobs, where we'd let Spark do the merges or the compaction of all the inserts, updates, and deletes to be applied on one side for a table, and then we'd give the exact same sets of inserts, updates, and deletes over to Ray, and they would both create their own read-optimized version of the table for our consumers to consume. We observed that on average, Ray was running in production without much of any manual intervention, about 80 to 90% more efficiently than Spark, which meant for us, for every gigabyte of input data that it processed, we were paying about 80 to 90% less to produce the final output result that all of our business intelligence consumers would query and consume. 80 to 90% cheaper in this case also meant that we could also be about 80 to 90% faster.
Oh, yeah.
And there's a little bit of a dial
That's a
there that you
huge
can
difference.
dial one way or the other. You can optimize purely for efficiency, and sometimes that comes at the cost of time to delivery. And you can choose to optimize for time to delivery and maybe pay a little bit more. But in general, they go hand in hand a little bit for this
Well,
product.
we've seen this historically, haven't we, with like technologies that make it easier to do something, faster to do something, and that then can result in almost like your ability to take more risk.
That's right. I mean, and risk in this case is kind of the risk to maintain larger data sets and to collect more data and to be able to safely deliver that data for consumption regardless of its egregious size to your data consumers for consumption. So without continuing to push the envelope about just doing these fundamental operations like data set merges faster and more efficiently and more scalably, at some point, our only solution otherwise would be to just ask our data set maintainers to just retain less table history and like, could you please stop sending us so much data? We don't want all of your business intelligence data, which isn't really an optimal solution for the problem.
So what have been the trade-offs of this then?
So one trade-off that we've observed and that I wrote about in an AWS open source blog previously has been, so far, Ray has slightly trailed Spark in terms of first-time job run success reliability. So when we do these so-called compaction jobs, where we're merging all of this data, the first time the job runs, as of the last, say, 30 days of average job run reliability for Ray, I think it succeeds about 99.7% of the time. While that's pretty good, Spark is still at, I think, about 99.92 or 93 or so.
Okay.
Right? So Spark's got 3 nines of reliability there. Ray still only has 2 and is still working on the third 9. But that's just first job run reliability. We run the Ray job again. It typically succeeds the second time, but every time that happens, it does eat into your efficiency savings a bit. And where do you most likely fail? Usually on some of your largest data sets. So that's something that we're working on closing up, and we've made good progress over time. Like the end of just last year, I think Ray was sitting at about 85% first job run reliability. So we've already improved it from 85% to 99.7% as of today here in October 2024. So we're optimistic that we're going to close this gap and hopefully even exceed the reliability of the Spark jobs that we're competing against.
I could get into how you're doing that, but I think, we're coming close to the time here. I wanted to just ask, how you're contributing back to the open source community. And that seems like a way you can, talking about how you can balance those trade-offs with the efficiency gains that you're trying to reach and trying to hit.
In the early days of the project, we contributed a decent amount back to the Ray core project itself, especially focused on improvements to their so-called AWS Autoscaler, which allows Ray to launch EC2 instances for its cluster on demand and return those EC2 instances. Then we contributed a bit to Ray Data, which manages distributed data frames for distributed data processing. And these days, and for the last couple of years, most of our contributions have been within a Ray ecosystem project called DeltaCat. And right now, unfortunately, the DeltaCat project, although it contains the full production implementation of our compaction job, it can't be run out of the box on any existing open source catalog because the only implementation we have of DeltaCat's interfaces for managing tables is for our internal data catalog. So one thing that we're working on actively right now and hoping to release going into early 2025 is an implementation of DeltaCat that works first for Apache Iceberg so that we can bring these same benefits of managing Apache Iceberg tables and creating read-optimized versions of Apache Iceberg tables, optimizing so-called Apache Iceberg merge on read and copy on write operations, in an equivalent fashion and let everybody in open source take advantage of the same efficiency gains and benefits that we've observed during our transition from Spark to Ray for this particular job type.
That's a pretty good example. So Patrick, I want to thank you for your time today. Thanks for coming by and talking to us about this transition from Spark to Ray.
Yeah, likewise. Thank you for having me, Alex.
If you like this video, please give us a thumbs up. And if you'd like to see more videos like this, you can always subscribe to our YouTube channel. We're on all the major social media platforms. You can always find us at thenewstack.io. We hope to see you soon.